to MEL science, more specifically, of course, MEL chemistry. My name's Dan, and here, if I just move that out of the screen for a second, here, to help entertain you a little bit, but also to walk you through some of the chemistry. Hey, Franco! Hello, Franco! My name's Dan, and to help you walk through some of the chemistry and explain some of the science and bring a little bit of it to life, hopefully, for you. Constantine, hello Constantine. So for those of you who are new today, first time on webinar, for example, I can't see you and I cannot hear you, but I can see what you write. Hello Hugo, hello from Silicon Valley, fantastic. I bet it's a lot nicer and warmer there than it is here in the UK, but we've had some sunshine here in the UK today, which has been absolutely lovely. So do let me know when you come on, type your name in. Sophia, hello Sophia. And Wendy, hello Wendy. And from Indiana, lovely, hello Sophia. Hi from Arta in New Hampshire. Hello, Arta as well, fantastic, lovely. So all from the States at the moment. Lucia, hello Lucia and Hugo. Yes, sun's out here. Hugo, don't show off Hugo. I want to come over and nick some of your sunshine. Hello George. London, hello London. Lovely to have you guys on. So we'll give you a couple of minutes just so everybody sort of get themselves sort of set up and ready and fixed. And Isabel, hello Isabella, and Brian and Steve's. So once again, just quickly as you're coming in, just to remind you, I can't see you, I can't hear you, but I can see you typing. So as we go through, Lincoln, hello Lincoln, Ashiana, lovely name. Maddox, hello Maddox. As you come in, I'll quickly check from time to time that I'm going too fast so that you understand everything I've said. And hello Joshua, and Isla, hello Isla. And so just check your understanding. And of course you can ask me questions. Please do ask me questions. I'm a teacher. Professional scientist, so I love questions, that's my job. So, without much further ado, Ryder, hello Ryder! And Joshua again from, good, cool. So today, ladies and gentlemen, what we're doing today is we're going to do some colourful chemistry. So this is the set that we're doing today. Hello Sophia, and my sister Mia. Hello sister Mia, hello sister Mia! So this is the one we're doing today, ladies and gentlemen, colourful chemistry. So it's a lovely, pretty piece of chemistry. Obviously some complicated little bits of chemicals in it, hopefully make that understandable for you. All right, so without much further ado, let's Leo, give me the question, feed me questions, and we even chuck in a couple of jokes for you, hopefully, along the way, this little voyage of science. And hello, Violet. Right, so without much further ado, we're going to switch cameras a little bit so we can do an equipment check. So we've got 3 experiments today, and there's quite a lot of chemicals involved. Okay, so quick equipment check. And for everything else. So we'll just start with the chemicals. So first chemical you need is the eosin. So there we are. So eosin, so that's a food colouring. Then we have annatto, another colouring. So annatto, eosin. Just check that you have these. And then the methylene blue. So a little methylene blue. Liquid soap, a little bit of liquid soap. And of course you can ask me lots of questions and check things as you're going through. So thymol blue, so here's our indicator thymol blue. This is sodium hydrogen carbonate, so sodium hydrogen carbonate. Then citric acid, so just from citrus fruits as well, that same citric acid, and I'll explain a little bit of that as we go through. Then you need the sodium hydrogen sulfate, so sodium hydrogen sulfate. And finally sodium carbonate, so this is sodium carbonate. Okay. So the physical equipment as well you need from your general pack, your starter kit, you need 5 of the little cups that come in your starter kit, so 5 of those. You need some milk. Now the milk doesn't make any difference really whether the milk is full fat, half fat, no fat, but it does need to be normal milk rather than soy, for example, etc. You also need a tray, your little tiny petri dish. You need the white tray, of course, from your starter pack. What if I don't have cow's milk? You can try it, Lincoln. If you try it with any milk, it's perfectly fine, but it works much better with normal milk if you can. But don't panic. Yes, whatever you've got, do try it. You need the little tiny pin. Now this is the little tiny paper clip, which we use to take the safety plugs out of the top of our reagent bottle. So I'll just take that out like so. You also need the little wooden stirrers. We can't see. Joshua, what can't you see? Josh, let me know what you can't see. Was it the paper clip? Only black screen. Is that? I'm not sure if that's just your computer. Video is good from my end. Yep. Okay. Sure. So you need some stirrers. You need some spatulas or little spoons. Little earbud. and you need some water, so you need access to some water. So I've got a little bit of water here, and it maybe put your water in again, the little jug, or the 250ml beaker rather it is, from the starter kit. Okay, now I've got the 3 experiments cards that we're going to do, so I will set up the first experiment and then put the rest of the equipment to one side, and then we'll come back. Okay, so before we begin, is that okay? Can I just have a couple of answers just to check the oil? I know it's very distant, it's funny, this kind of sort of teaching. How many bottles do you need? Bottles of milk. Oh, sorry, man. Joshua, is everything okay? Maddox, you only need a little bit of splash of milk. I think if that's the milk you're referring to, Maddox. You just need really about 100 mils, if that's okay. Right, is that okay? I've got to ask you because I can't see you. I'm so sorry I can't see you. This is so cool. You're very Sophia. You're welcome. We haven't even started the chemistry yet. So, if you would like, Stephanie, can you go over the slides in? Yes, of course. Yes, I will do. I'll just go through that one more time for you guys. Just one more time, just to make sure you've got all the bits and pieces. Okay, with you. So we'll just do that very, very quickly. You want the eosin, the red dye, eosin. You need the yellow dye, the annatto. You need the methylene blue. You need soap. It's a liquid soap. And we have the thymol blue. This is your indicator. Okay. How much milk? About 100 mils, Nicholas. About 100 mils. So literally a little bit in the bottom of a cup. Okay. All we're going to do is we're going to put the milk into the Petri dish and then do a little bit of chemistry with it there. Sodium hydrogen carbonate. Then the citric acid. And then the sodium hydrogen sulfate. So hydrogen sulfate. And finally, thymol blue's gone off place, is sodium carbonate. So sodium carbonate. Right, and then the stirrers, your spatulas, and the paper clip to push the safety plug out, and 5 cups. You need, whoops, I've just chucked them all over the place now. So 5 of these cups, okay? So we're going to do the colour changing milk first. So we're going to do the colour changing milk first, okay? So I'm going to put everything else to one side. Now don't worry about the other things I had there. They're for demonstrations for you guys a little bit later. So put that to one side. So we're going to do colour changing milk. So for this one, for the colour changing milk, okay, so we're going to start with this one. We need the red food dye, the yellow food dye, and the methylene blue, and you need the milk. Okay, and you also need the soap, so a little bit of soap for this one. So I'm just going to move that over here, put those there. Okay, move that to one side, move that, and that, and that, and that, and that. And then we have the soap, and then we have our cotton bud, and a paper clip. Cool, and there, whoops. Right, hopefully that's everything sorted. So for this one, right, hopefully, is everybody okay? Just give a couple of seconds for that one to set up. Right, so what I'm going to do, why is soap used most in chemistry experiments? Leo, soap is what's called a surfactant, a surface active agent, okay? And what soap does, in fact, I've got a little slideshow, just a brief couple of slides just to show you to start with. So here's our little water boatman. So in our chemistry today, what we're going to do is we're going to do 2 different parts of chemistry. We're going to look at surface tension in molecules, and that's what's called surface tension. There's called van der Waals forces, and I'll explain that in a second. How many years of college does it take to become a real chemist? Sophia, to become a real chemist, you need to have gone through at least 3 years worth of university, and then if you specialise, you get an MSc, or if you want to specialise even further, go and get a PhD, or you can just go into teaching and teach it for years and years and years. I mean a chemist. Yeah, so in the UK, a degree to do chemistry is usually about 3 years. In America, it tends to be about 4 years, with some of your undergraduate studies. Anyway, so off on that. So here's our little water boatman. I hope that some of you have noticed these little creatures. Can you see how the water, look, is bowing down under its little feet? The water seems to be bending, okay? Now the reason that does is because water has a skin, and the skin, the water molecules lock together, and they're called van der Waals forces. Now don't worry about the detail of all that, but basically some parts of molecules are positive and some sides of molecules are negative, and the positive and negatives kind of stick together, and they call a little bonds. They make little weak bonds called van der Waals forces, okay? And that was actually named after this wonderful sounding physicist actually called Johannes Diederik van der Waals. I'm trying to say that in my best Dutch accent, so Johannes Diederik van der Waals. And he actually won a Nobel Prize, really interesting character, but that's what these little forces are named after, because he's the person who said, right, this is how molecules kind of stick together. And what we're going to do in our first experiment is look at how we can break them apart and do something really cool with them, I think. And we'll come on to that one a little bit later. So, without much further ado, let's get the show started. Right, so in your little Petri dish, you get your Petri dish, you then pour into the Petri dish some milk. So about half fill the milk with Petri dish with some milk. And now what we've got to do is we've got to take the safety plugs out of the top of each of these dyes. So I'm going to start with the methylene blue. So if you unscrew the methylene blue, can anybody tell me what I have forgotten? Which two pieces of equipment have I forgotten to mention? Anybody? Which two important bits of equipment have I forgotten? You've all got quiet. Safety glasses, indeed. So if you wouldn't mind, slap on your safety glasses and gloves. Yes, indeed. So you've got some little gloves. I'm going to use some slightly different gloves because my hands won't fit in that. So, get some of these gloves out. So if you get your gloves on and get your glasses on, that would be great. And all these gloves seem to have stuck together in mine. Supply. So pop your gloves on and pop your, yes, Lily, thank you. Maddox, well done. Franco, excellent, spot on. Mohammed, what kit is this? Mohammed, I think you might have joined a little early. It's the colourful chemistry one, Mohammed. Colourful chemistry. So if you haven't got it, don't panic, because all of these webinars are filmed and you can catch them, or anybody can catch up with them a little bit later. So if you just want to watch and listen to some of the explanations now live, or ask me some questions, you can do that now. Okay, cool. Right. Back to the knitting, as it were. So we undo the lid on this one. And so if you get your little tiny paper clip and stick the paper clip into the... Now you might have to wiggle it about a little tiny bit, okay, wiggle it about a bit to get the plug out. Now I'm going to, in between each one, just give the paper clip a little bit of a wipe, okay. So that one's that one. Then we're going to get the liquid soap. So depress again the little tiny safety plug in there, like so. Now that one came out quite easy. Sometimes you might have to give it a real poke, okay. The next one... Okay, the next one is eosin, so I'm going to give that little tiny wiggle, and that one came out quite easily, which is great. And the next one is annatto. Ebony! Hello, Ebony! Poke that in like that. And then finally, we've got the... Oh, we don't need the sodium carbonate for this one. We just need that. Okay. Move that to one side. Okay, cool. Everybody seems to be okay. Right. So what I used to do first of all is put about 1 or 2 drops of each of the coloured dye into the milk. So just put like 1 or 2 drops of each of the dyes into the milk around the dish like that. So maybe one there, look. One there. I'm going to put one there for good luck. And then the red one, I'm going to try the red one here and put that red one there, red one maybe in the middle, and then maybe one to the side. Now you'll notice that as these drops go in, they kind of stay more or less where they land. A little bit of spreading, and then last but not least, look, some of the yellow one. And that one spreading only a little bit. Okay, cool. Right, so now what we do, can you see, is this, Ebony, it's not, no, this is not the polarized light kit, Ebony. This is the colourful chemistry one, okay, colourful chemistry one. So if you get your cotton bud now, and to one side, place some drops of washing up liquid or washing soap onto the bud like that. So you're just creating some little drops, about 3 or 4 drops, okay, onto the bud. And if you then just touch very gently somewhere on the surface of the milk and see what happens, okay? Yeah! Whee, woo! And then maybe again look and touch it there again and there again. And you should, I hopefully, see some really rather beautiful sudden changes in the nature and the structure of the surface of the milk. Okay, and when you've done so, it's really rather beautiful, that really beautiful colour sort of mixing. And if you want to go a step further, can you please go slower? I can't catch up. Eshni, no problem at all. Eshni, always. It is like a little bit of an explosion, Ebony. It is, yeah. So just touch the surface of the milk with the washing up liquid, and if you want to take it a little bit further, you can actually put some direct. Can it have an explosion if you had another chemistry element? And you can add, for example, like copper. Leo, yes, of course. In some of the other MEL chemistry kits to come, like pure water, for example, and oxyhydrogen, we've got some really nice little explosions, which are really super cool. This is beautiful, different chemistry. This is looking at acids and alkalis, indicators, and here's surface tension. So what I'm going to do, look, it's going to drop. Whoa, 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 look at that. And that, you can see, is really rather beautiful chemistry. So what have we done there? What we've actually explored here, isn't that colourful? It worked great with almond. Lincoln, that's lovely to do. That's really cool to know. Thank you very much for that. If it worked really well, all liquids, of course, as I said, have a surface tension. Okay, I'll just go back one little slide here. Look. So they all have this sort of surface tension, and when you put the washing up liquid onto the, if I just go back one more slide, when you put the washing up liquid, that all those molecules that are linked slowly together, so all little water molecule, they're kind of stuck together by these weak van der Waals forces, and as soon as you put the surfactant in, the washing up liquid, it broke all of those little bonds, okay, and that allowed all of the colours and the dyes to mix more cleverly. Opening, no problem. What was the orange one? Ashani, the orange one is called Anato, and it's a food dye. Very often, if I just switch to that one, it's called Anato. That's the yellow one. Okay, that's a yellow food dye, effectively. Okay, is that okay? Did that work for everybody? Is that all right? You've all gone very quiet. It's all so silent. Yes, Sophia. Yes, I got a yes. Yes. Okay, cool. Franco, yes. Lily, yes. Lovely. Thanks, guys. As I said, smashing off. Thank you. Great. As I said, I can't see you and I can't hear you. It's so difficult as a teacher to sort of teach in a room with there's hardly any content apart from his words, but your words mean so much. So thank you very much. Lucas, great, lovely. Okay, so let's pop the lids back on these ones, and then I'll explain a little bit more of the chemistry and maybe tell you a joke or two. So pop those to one side. Okay, so pop these things to one side. Do they use thin colours in fireworks explosions? Leo, no. In fireworks, the colours in fireworks are made by different metals. If I just switch here to just answer that question really quickly. So some of the metals they use in fireworks, for example, are, for example, like copper. You might have heard of copper. That's often used in fireworks. And of course, you've got barium is often used in fireworks. And sodium and potassium are often used in fireworks. And when they burn, these metals, when they burn, give off different colours. And beautifully, in one of the MEL kits that you may or may not have had, or hopefully coming up, you will actually replicate some of those colours by burning some of the metal powders in the flame to show you those kind of colours. On a chip, why are there different colours on every model? Sophia, every model. Well, the reason the different colours on the periodic table is that here we have what I call the transition metals. Here you have the alkali metals, you have the alkali earth metals, and then you've got, of course, the periodic tables, all the elements that make up everything in the universe. And we either have metals or non-metals. And on this side here we have the non-metals. So about 20% of all the elements are non-metals. And then you've got the metalloids, the pink bit of the metalloids. So some of them, some slightly metallic properties, some non-metallic properties. So they're the metalloids, and then we have the non-metals, and then you've got the big radioactive and the rare earth elements down the bottom, okay, and the so-called lanthanide series. Mg and Br for fireworks too. Yes, of course, Arthur, yeah, definitely magnesium for like white things, and Ba, yes, perfect, yeah, absolutely. Okay, cool, right. So what I'd like to do, just very quickly, before we get into the next bit of chemistry, the experiments rather, is just explain a little bit of the chemistry if I just quickly scan through those. So basically, the chemistry that we're going to do now is moving, it's totally different, but it looks at a different variation of coloured chemistry. We're going to look at water and acids and alkalis. So if you look at water, everybody knows it's H2O, okay? So everybody knows it's H2O. If you separate the molecule, you get hydrogen ions and you get OH ions if you separate the molecule. Now, when we look at acid, Sophia, on the corner of each box, on the top corner of the table, there is a blur. I can't see what it is, that. I'm not sure. I don't know, Sophia, maybe, Razal, if you could just check what that might be. I don't know whether it's a blur, it doesn't seem to be clear to me. Okay, when we look at acids, they have lots of hydrogen ions. So when you split up the water molecule, remember, you've got hydrogen ions. And when you look at alkalis, they have lots of OH ions, okay? OH minus ions. Arthur, nobler for us. So yeah, sometimes there's some odd things that go on in different people's sort of computers, and sometimes it is my fault. So don't feel afraid to say, Dan, I can't see this. It doesn't make any sense. What's going on? Because sometimes it is my fault. But I think, oh, the atomic number is a bit of a blur. Sometimes the camera doesn't focus quite sharply on the periodic table, and that's it. That's the only reason, I think. Okay, cool. If we move on a little bit. So if baking soda and Leo, citric acid mixed with copper, it will have the... Not quite. So if you react sodium hydrogen carbonate, which is basically baking powder, with citric acid, you get sodium citrate, a bit of CO2 and some water, okay? And it's a nice foamy reaction, but no explosion. You have to have a different set of chemical bonds breaking and forming to form an explosion. And then the copper in that wouldn't react to give any colour. You have to do some curious things with copper to make it reveal its colourful nature. Okay. Right, just very briefly, the pH scale, of course, registers everything that is either acidic, and you can see here on acidic, it's really red, and the numbers are very low. And then if you go to the other side of the pH scale, it's very basic, and the high numbers are very high, and it's kind of purpley coloured. So we go from reds and yellows and greens to purples, okay? And we use things called indicators to tell us whether a solution is either basic or acidic. Okay, so special chemicals called indicators that tell us whether things are basic or acidic. Right, let's have a play with the experiment then, and get that one done. So let's move that one out of the way, and let's have a play with an acid-basic reaction. So the first one we're going to do is we're going to do this one here. Okay, so we're going to start with acidic patterns. Okay, so acidic patterns. You're very welcome, Leo and Sophia. Lovely. Okay. Right, so for this one, you need, again, your other Petri dish, a little bit of a Petri dish, okay? Well, a little bit of a Petri dish, you want the whole Petri dish. Shani, of course I can, of course, Shani. I'm just going to go through the chemicals that you need. And you need some water. Now, you need the sodium carbonate for this one, some water, obviously, some sodium carbonate, so just find your sodium carbonate, okay? You also want the thymol blue for this one, so thymol blue. Okay, so sodium carbonate, thymol blue, and you also want the sodium hydrogen sulfate. So if you can find your sodium hydrogen sulfate, so that's this one here, sodium hydrogen sulfate, sodium hydrogen sulfate. Okay, and we also want our little stick, so a little bit of a stick. Right, so I'll just let you guys and girls get that up to scratch. Okay, but anybody like to hear a joke? Anybody like to hear a joke? Just while we're getting things sorted and settled up. Anybody like a little joke? It's all gone quiet again. You guys! Leo, excellent. Okay, right, a whole variety of different jokes. You've got to listen to this one, okay? So here it comes. Thank you, Lima. Thank you, Maddox. Thank you. Excellent, Sophia. Okay, right, listen carefully. I, for one, really like Roman numerals. Get it? I, for one, really like Roman numerals. Get it? Thanks, Arthur. Thank you, Ligon. I didn't say they were going to be great jokes. I just said they were going to be jokes, okay? I don't get it. Sophia. Sophia. Sophia, if you look at Roman numerals, okay, the first number is an I, okay? The first one is an I. So I, for one, like Roman numerals. Sorry, Sophia, I didn't mean to kill the joke, but hey. Okay, let's move on. Okay, one more for you. Now listen carefully. I entered 10 puns into a pun contest, hoping one would win, but no pun intended. Get it? I entered 10 puns into a pun contest, hoping one would win, but no one did. No pun intended. Get it? No pun intended. Maybe I did 11. Hey, Arthur, you're very welcome. Hello. Hey, so yeah, cool. Right, I'm glad I made a little smirk here and there on the faces of all you students around the world today. Cool. Right, let's crack on. So for this one, okay, first of all, what we need to do is now we're probably going to have to undo the safety plug. So the first things first, if you get your sodium carbonate, carefully look at sodium carbonate. sodium carbonate. Now undo this one, and we've got to take the safety plug out of this one, as per usual. So look the safety plug in this one, and just give it a little wiggle, push that in. Sometimes they are a bit stiff, so this one's proving a little bit awkward today. A little stiff, but there we go, almost there. Pokey poke, poke poke. I think that's it. Yeah, there we are. So poke that one out. Again, it's a good idea to, it's very funny. Thank you, Lily. It was attended to. There you go. Hi from Abby and Ben. Hello, Abby and Ben. I didn't see you before. Have you come in late? Don't panic. Don't panic. So thymol blue. So again, let's just take the thymol blue one out, and there's a little bit of liquid coming out of my one. Just give that a little poke, just to put the, hi Archie. Cool. And then the hydrogen sulfate. So a little bit of the hydrogen sulfate again, give that a little pod. Because of course these packs come in the post, and it's designed to prevent any leakages or spillages. And what you might have thought about these little tiny, these little wads that come in each of the packs, they're designed to soak up any spillages that might happen in the packs. Okay, great. If everybody's ready, then first thing first, what we're going to do is we're going to start with the sodium carbonate. Okay, so take your sodium carbonate, and you want maybe 3 drops into the Petri dish. So 1, 2, 3. Oh. Okay, so 3 little drops into your Petri dish. And now what you need to do is half fill it, approximately half fill it with water. Okay, so half fill that with water. Okay, so half fill that with water, and then give it a little bit of a stir. So just give that a stir to mix those little drops up with the water. So give that a little bit of a stir. Okay, and now what you need to do is get the thymol blue. So the thymol blue, and that's this one, you want 10 drops of the thymol blue in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. And that you see is given already a really rather wonderful blue colour. So now give that a nice mix around, so make it a nice uniform blue colour. So give that a nice mix around, so you should have a really lovely uniform blue colour there now. Okay. Sophia says, are any of the things that you are using on the periodic table? Yes, everything. Everything is on the periodic table. Everything in life, everything you see is made of things on the periodic table. This is the ingredient, the recipe book for life. Everything in the universe has to be made of what's on the periodic table. That's what makes this so wonderful, an awesome piece of chemistry. Right, now cool, next thing. If you put 5 to 7 drops of the sodium hydrogen sulfate, so 5 to 7 drops of the sodium hydrogen sulfate in different places around your dish. So okay, 1 there, look, 1, 2, 3, 4, 5, 6, 7. Oops, a little bit more. Now this is the gentle bit, so be really due. Why is the thymol blue purplish for me? It should be a blue-purple thing. It looks probably bluer on my camera because of the way in which the data is streamed through and translated into an image for you at the other end, okay? So it does actually a purpley blue colour. That's absolutely right, Shani. Okay, so now if you take your little stick and very gently trace through the liquid and see what happens, okay? So very gently trace through the liquid like that, and slowly but surely you should start to see some really beautiful little tiny swirls, little swirly magic oranges and yellows and greens, and look at that. How beautiful is that? Isn't that magic? So you get some lovely little tiny swirls of oranges and yellows, some really wonderful little tiny loops and whirls. And then slowly, of course, the liquid is turning yellow. Okay, so it's actually turning yellow, and all the blue, by magic, seems to be disappearing. I can give that a nice big swirl. So actually look at, if you give that a nice big swirl, isn't it, Lily? It's really cool, isn't it? So I can mix that all up. Now the whole liquid has gone a yellow colour. Now give that a good mix, so you've got a nice uniform, looks like a bit like pea, bee coloured, okay? And so that's gone yellowish colour. Can we pour this down the drain for disposal? Is it safe? Which ones are not safe to pour? Leo, all of these things can be poured down the drain without any problem at all. And they're perfectly harmless, these chemicals. Okay, and then with running water and make sure whilst it isn't turning yellow. If it isn't turning yellow, Lincoln, if you just give it another stir, give it a bit more of an energetic stir, and hopefully it should turn yellow. Now what we can do rather beautifully is we can reverse it and go back to blue. So here, now this substance here, I'm going to introduce these terms, it's a base. Okay, this is a basic or an alkaline substance, okay? And what we can do, if you put another 5 drops, say 5 to 7 drops, again, into the yellow, you can see, oops, blue is magically starting to reappear. Okay, so the blue is then starting to magically reappear. And then if you then give it, like you did the last time, give it another little gentle swirl around, and suddenly you should see the blues, the yellows go into blues in little tiny swirls, look. Like that. Is that not, or is that not beautiful? Beautiful little bit of chemistry. Indicator chemistry, which will explain. What does it call the blue? The blue itself, okay, the indicator, this is called a chemical, it's called thymol blue, it's an indicator. And now it's going the other way. I'm going to explain that science to you just in a second. If you wait for 3 seconds. Now it's yellow. Lincoln, excellent. I know it would be eventually. Okay, so here we've gone from yellow back to blue in our little swirls. And what you've probably realised is that you can reverse that again by putting in a bit more acid, okay? So the acidic solution, so this is now an acidic solution, like a citric acid, for example, and we can try and make it go back to yellow, look. And I think, well, I'll ask you actually, I put another, say, 5 drops back there, like so. And then, again, repeat that process. And again, the little beautiful yellow swirls come back. Oh, not quite. I think I need to put a bit more of my sodium hydrogen sulfate in there. So just put a bit more of that in there, like so. So if it doesn't come back, it might be that you've put a little drop too many or too little of the acid or the alkali in your solution. But there again, look, you can see those beautiful swirls coming back. How lovely is that? So what chemical compound is in the Petri dish from the periodic table? Leo, the Petri dish itself is made from a chemical called compound, a plastic called polystyrene, okay? Polystyrene, I'm going to move that back to sort of yellow, so I'll turn that back to yellow. Leo, lovely question. It's called polystyrene, okay? So poly means many, and styrene is the group, the little molecule, the molecular what's called a mer, okay? And polystyrene is basically made of carbon and hydrogen. So it's basically made of these two things, so carbon here and hydrogen. So big, long, complicated chains of carbon and hydrogen. So that's what that dish is actually made of. So polystyrene is the molecule, so you can look that up, and you'll see that polystyrene is just made up of those two elements in different combinations. Is that okay? Cool! Did that work? Did that work for everybody? Is that okay? Is that pretty? Yay! Got one yes. Leo said yes. Isabel says yes. Yeah. I've got a yeah from Isabel. And Marek says yes. Arthur says yes. Lovely. Yay, 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 and yay, and yay. Very pretty. Lovely. Excellent. Thank you so much, guys. And Hugo, and Constantine, and Lily, and Franco. Thank you so much, guys. And girls, if I then just quickly go to the slide, so I can just explain this chemistry. So what we've looked at, more other questions. Leo, no problem with the questions. No problem with the questions, Leo. I love the questions. Yay, Franco and Sophie. Yay! So we're looking at indicators, and if I just quickly click on to the next slide. And basically what happens, remember I said, when you split water up, okay, it goes to hydrogen ions, and those are acidic, and then hydroxide ions, and those are alkaline. So the pH scale here, look, you see, at one end, the red end, this red end just down here, got loads and loads and loads of hydrogen, so it's lots of acid, it's very acidic, and then increasingly, if you go then towards neutral, so in the neutral you see it's pH 7, that's green coloured, you've got equal amounts of OH and H, and then deeper into the other end of the periodic table, the pH scale rather, not actually in the periodic table, it's behind me, you've got OH, lots of high concentration of OH, and it's purple, and the pH has gone up as opposed to gone down. Why are there little bubbles? I don't know, I haven't got any little bubbles in mine. It might be that as you're turning it around, you could just trap a little bit of the air, and there might be the odd bubble in there. So coffee is acidic. Yes, coffee, it's although it's a very dark solution, it is actually ever so slightly alkaline, Coffee is slightly alkaline, I believe. But again, that depends on how much milk you put in there. It depends also on the water and all sorts of stuff. but if you add milk, it will change. Yes, it will, indeed. Milk is, of course, very alkaline. It's got lots of calcium in it, and it's got lots of fats and all that kind of stuff, but milk itself is ever so slightly alkaline. Yeah, that's exactly right. Okay. So on the periodic table, what does OS mean? Osmium, that is the element osmium. So you spotted this one here, so it's element 76, and that stands for osmium. So that's one of the transition metals, okay? And you can actually put osmium in rings, to be honest. So one of really expensive, it's one of the most expensive elements actually, and it's also one of the densest elements as well, though they are very heavy, osmium. Okay, cool. Right, so where are we going from this? Let's move along a little bit further. Brine shrimp, how do they hatch on their own? All creatures, sorry Leah, all creatures will hatch on their own. So any creature that is in an egg, that's through the basic process of growing up and expanding. At one particular point, they either have to break through the eggshell itself or the little sort of cellular structure membrane that's enclosing it, so they all break themselves. Okay? Right, so we used... This is universal indicators in thymol. So we use thymol blue, so thymol blue, strange kind of thing, but it's what's called an indicator, okay? And there are lots of different types of indicators. So here's a little really pretty graph that shows you phenol, phthalene, bromothymol blue, thymol itself, and so on and so forth. There's lots of different indicators that change colour, and if you want to do something really cool at home, if you haven't done this already, is get a red cabbage, chop the red cabbage up, put it in some boiling water, extract the juice, and that juice is full of what are called anthocyanins, and they change colour too, and they're called indicators, okay? Right. Now, before we get onto the sugars and stuff like that, let's have another little go at experiment number 3, and maybe a joke before then. Okay, cool. Handy cam, let's go to face cam again. Right, this is one of my experiments. This one. Oh, cool, cool. Nice one, Leo. Right, is everybody okay? We're going to do like a quick joke before we get on to experiment number 3 and explain a bit more about acids and alkalis, right? Yay! Lincoln, excellent. Okay. How about a knock-knock joke? How about a knock-knock joke? Everybody ready for a knock-knock joke? Sophia! Okay, right, here we are. Knock-knock. For you out there. Knock-knock. I am. You don't know who you are? You don't know who you are? I am, huh? Hey, who are you guys? Leo, I'm delighted to know. See, Leo, gotcha. Excellent news. Right, cool. Right, let's get on to experiment. It's one of my favourites. It's not my absolute favourite, my best. I'll save my absolute not favourite joke to the end. Okay, so let's move on. Let's get to experiment number 3. Okay, so experiment number 3. Right, if I just change the view. So we'll move that one again out of the way, hopefully without spilling too much of it. And put the lids back onto our various chemicals. So you will need, for experiment number 3, so this one here, we're going to do magic liquid. So this is magic liquid, okay? So this is experiment number 3. So for this one, you will need your thymol blue again, so thymol blue. You'll also need your beaker, so your big beaker from your starter kit, okay? And, actually, hang on. So we don't need the milk anymore. You need some water, okay, so will you have spent at some point making the volcano an explosion? Yes, Leo, yes. If you, all these webinars, I go through all of the different MEL experiments, the chemical ones in particular, and there are definitely going to be experiments. And very often what I do when there's an appropriate one is I'll do a demonstration as well on top of the experiments, just to sort of show you something fun and interesting, on top of the MEL interesting stuff like that you will have already done. Okay, so here, so what have we got? We need some water. We need our beaker, so 250 ml beaker from your starter kit. You need the thymol blue. Now here we need a range of different chemicals. So we need the citric acid. So here's the citric acid. Okay, so citric acid, one of them. You need the sodium hydrogen sulfate again. So sodium hydrogen sulfate again. Okay, so citric acid, I'll just leave those there so you can perhaps see them. So citric acid, sodium hydrogen sulfate. You need the sodium carbonate again. So this is the sodium carbonate. Now be careful with this, guys and girls. There's sodium carbonate and then there's sodium hydrogen carbonate, okay? So there's sodium carbonate and there's sodium hydrogen carbonate. So now we need This is the sodium. Now you notice the sodium hydrogen carbonate is a solid. This isn't a liquid. So this is sodium hydrogen carbonate. So I snuck a little extra H in there for you. Okay. Everybody okay with that? Now we also need then our 5 cups. So 1, 2. Now they won't all fit on my tray here, so I'm going to put those just in front. 1, 2. Move that to one side. 3, 4, 5. Okay. Now you also need a separate stirring and your spoon. So we're going to need a spoon. So if you grab your spoon and also your stirrer and your little tiny paper clip. Okay. Everybody okay? Is everybody okay? I hope. Just leave that for a second. Let everybody give you time to sort of set that all up. How is the sodium bicarbonate liquid? I thought it was solid powder. Leo, yeah. All of these liquids can be solid. And so the liquids you see are the solids basically in solution. So they've just added, in most cases, the solid to water, so distilled water, deionized water rather, and then turned it into a solution. Good to go, Lily. Excellent, excellent. I'm so excited. Excellent. This is very pretty. It's very magical, this one. Very magical. So first things first, what we need to do is get your thymol blue. So get your thymol blue and put one big scoop, so the big end, so big scoop, okay? If I put lemon juice in decabbage, will it water? Yes, it will, Ebony, and I'm going to show you a little trick at the end, okay? Yes, you're absolutely right. So one big, very generous scoop into the beaker like so. So one big scoop in that. And then what we need to do is fill that up then with water, so normal tap water do. No problems, Ebony, no problems. So fill that up full of water, okay? And then give that a really good stir. So let's give that a nice stir. So mix that all around. So now what we've got is an indicator solution. So this is an indicator solution. Remember what I said? That the group of chemicals that tell you whether something's acidic or alkaline is called an indicator. Okay, and they change colours. And they're all different, so they do different colours for different pHs. Okay, so now what we need to do is put the chemicals into our little cups. So first things first, what you need to do is put sodium hydrogen sulfate. So if you get the sodium hydrogen sulfate first and put 10 drops. So put 10 drops in the first one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so put 10 drops there. And I'm going to leave the little cap behind them so you can actually see, or maybe it's in front of it. Let's just put that to one side. Okay, a little bit like that. Okay, now you want the citric acid. So if we get the citric acid, now I don't think I've taken the plug out of this one. So again, we've got to take the little plug out, so don't forget why not use cylinders, or does it not matter? It doesn't really matter, to be honest, Leo, it doesn't matter. Nice question though. So take the little plug out of that if you haven't. Oh, this one's just popped in. So what we want here is 5 drops of this one. Be very careful with these, okay? You want to put specific and very precise quantities in each one. Okay, so 5 drops of 1, 2, 3, 4, 5. Okay, so that's 5 drops of citric acid in there. Now for the middle one, okay, we're going to put 2 chemicals, the sodium carbonate and the citric acid, okay? And you might see some fizzing in that one, okay? So here's the sodium carbonate. Now you want to put 5 drops of each, so 5 drops of the sodium carbonate. So 5 drops in there. 1, 2, 3, 4, 5. And then 5 drops of the citric acid again. So the citric acid is going in this one as well, okay? So put 5 drops of that. 1, 2, 3, 4, 5. And very prettily, you should see a little fizzing going on, a little bit of chemical magic going on there. That's because you're adding an acid to an alkali, there's a bit of neutralization, and so some carbon dioxide is coming off. Okay, so for our fourth one, you're going to put some sodium carbonate on its own. So sodium hydrogen carbonate. Okay, so this is the sodium hydrogen carbonate. Okay, so you want to put 1 small spoonful. So here, look, the small spoon, 1 small spoon of the sodium hydrogen carbonate. So 1 small spoon, again, sodium hydrogen carbonate into the fourth one. So that's why you do it over the tray, so you might spill a bit of the powder, okay? So 1 small spoon in there. So that's the sodium hydrogen carbonate. And then in the last one not least, it's the sodium carbonate again. So sodium carbonate again. And what we're going to do is put 5 drops. So 5 drops of the sodium carbonate into that one. So 1, 2, 3, 4, 5. Okay, cool. Right, so that's the sodium carbonate. Out. So that's our basic reagents all added to our little cups. Now what we're going to do is add our magic liquid to each one and see what happens. So you want to put the same quantity, so about 50 mils into each one, okay, of our liquid. Let's just see how magically this changes, okay? Look at that, lovely coloration there. Beautiful red colour suddenly appears. And then a rather wonderful little orangey colour appears. Now we've got a yellow colour. This liquid doesn't need to seem to know what it wants to do. Then we've got a kind of bluey green colour. And then last but not least, oh, look at that, wonderful, wonderful blue colour. How beautiful is that? Isn't that awesome? Hopefully everybody's seeing that wonderful transition of all those wonderful colours. Is that good? You guys all got some quiet, isn't it amazing? Yes, you can. You can, of course, Leo, yeah. Now that's something, so keep those liquids, Leo, keep those liquids there, and then you can play around by adding a couple of drops of each of the different chemicals in the powder to each one of those liquids. Is that okay? Yes, absolutely, Leo, exactly that. Yes, of course you can. Okay, so let's explain what's kind of going on there, okay? If I go back a little bit. Okay. So these chemicals, the thymol blue that we use, so this thymol blue stuff here is what's called an indicator. It's called an indicator. And you have universal indicators, are a mixture of different types of indicators because they have different colours. Can you see on the bottom there, it shows you the different colour ranges that each indicator changes in the presence of an alkali or an acid. Okay, so you have lots of different indicators. And really, one of the interesting things about all of this so far is we're looking at alkalis and acids. And I just want to have a quick look at some acids and put it into context for you. Hopefully, this is a horrible picture, some really awful teeth. So some really disgusting teeth. Ah! But the reason that those teeth get there is because of this. So when you eat loads of candy and sweets, that's made of what's called sucrose, and sucrose breaks apart to form glucose and fructose, okay? And what happens then is the little bacteria in your mouth, they go, oh my gosh, there's so much lovely food, and they break down. They love sucrose, they love sweeties, okay? They love sweeties, and when they do that, they break down the sucrose into different acids. I don't worry about the chemistry too much, but they break it down to lactic acid, pyruvic acid, formic acid, and acetic. So in your mouth, those little bacteria eating all the glucose you give them and all the fructose, and then they're breaking it down to all those acids, and it's the acids that rot your teeth. Okay, it's the acids that rot your teeth in that kind of process. Okay. What's the difference between a universal indicator and a regular indicator? Sophia, the individual chemicals, like for example, if you're red cabbage, you chop that up, the chemicals that come out of that are coloured are called anthocyanins. So that group of chemicals, they change in a particular direction because of the nature of that particular chemical, okay? But if you put in thymol blue, that's a different chemical compound, and it changes colours in a different way. And you can mix all those indicators and therefore have what's called a universal indicator. Hey, so quick thing, I will leave early today because I'm not feeling very well. See you next week. Ebony, I hope you feel better. Please, please, please get better soon. And thank you very much for joining. Thank you. If you want a certificate, if you'd like a little certificate from me, personalised certificate to say you've joined and a little bit about the chemistry from me, you just got to go into the link. They'll be put up in a minute, and you can get a little certificate, and I send that to you to say thanks very much for joining. I hope the chemistry was okay. Okay, cool. So just a quick history trip. Right from the beginning, the whole history of acids and alkalis and the study of pH has gone back hundreds and hundreds of years. Started with Yabir in Haiyan, and he decided that he could understand what acids were and what alkalis were. In terms of group, in terms of types of chemicals, but he didn't know what they were actually there, but he put them into groups effectively. Then you have this very famous chemist called Antoine Lavoisier, and he decided that he thought that acids themselves had oxygen in it. I guess not. Wow, I thought all these discoveries were modern. No, Sophia, no. The whole science of chemistry is very complicated. The chemistry of this has actually taken hundreds and hundreds of years to fully understand, okay? And so Antoine Lavoisier and his wife, you can see lurking in the background, Marie Lavoisier, he thought that acids had oxygen in them. And then along came Humphrey Davy, and Humphrey Davy thought that he was wrong, and he said, actually, I think it's something maybe to do with hydrogen, and I've just moved my little thing around so I can't see it. So he proved Lavoisier wrong. He was a complete lunatic as a scientist. And then you have Justin von Liebig, and he said, actually, I think we can group acids and alkalis in these particular areas. And then came along Svante Arrhenius, and Svante Arrhenius said, right, acids and alkalis have either lots of hydrogen or lots of OH. So he's the first person to really say that they had hydrogen and OH. And then you had Bronsted and Lowry, and they came up with defined acids and alkalis even more closely. And so it's a long history. It took a lot of people, a lot of thought to get to understand what acids and alkalis were. And then the pH scale was actually discovered in a brewery, the Carlsberg Brewery to be precise, by this guy called Søren Sørensen. Lovely, lovely chemist, lovely scientist working in a brewery. And he thought, well, we actually need a scale to put all these acids and alkalis. So he's actually invented the pH scale that we saw right at the beginning. Okay, I just thought just leave on some examples of acids. Of course, DNA. We're all made of DNA. It's all our genetic material. It's deoxyribonucleic acid. So it's actually acids are all around us. And why are all these names so complicated? Severe. It's the nature of history and the nature of people giving birth and giving some really complicated names from all over the world, of course. You know vitamin C, we played with citric acid today, of course. At the bottom, look, here's you've got citric acid, on the other side you've got ascorbic acid, and of course I've got ascorbic acid, vitamin C. And all of these are acids in our day-to-day sort of life, and of course we can tell those by indicators. And then formic acid, you've all probably seen stinging nettles, and stinging nettles stick into you, and they put in formic acid, and there's little horrible little stings, and also histamine there. And these little needles look a little bit like that. So that's a close-up of a stinging needle, ready to stick a little bit of formic acid into you. Okay, and say, hey, back off, I don't need to be in your presence anymore. Okay, cool. So I hope that was okay. Okay. Is that all right? Any questions? Any questions? Venus flytrap. No, Venus flytrap, they don't inject, Leo, lovely question. Venus flytraps don't inject anything into, what happens is a fly lands on the Venus flytrap and it's got 3 little hairs on both sides of the thing, and you trip them, and it trips, and so it starts a little chemical reaction going. If you trip 1, tick, 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 and if there's nothing happening, the plant goes reset. If you trip 2, tick, 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 and the plant's getting ready to get you, and if you trip 3 little hairs as it's walking about on the leaf, if you trip 3, whoom, bang. And then what happens is through the leaves, they leak into it digestive enzymes which then digest the fly and take out all the nutrients that it needs. What is your favourite thing on the periodic table and why? I don't have a particular favourite thing, Sophie. The periodic table is magnificent. All these elements are absolutely amazing. They all have wonderful stories to tell. It's too difficult. Some of the elements are a little bit boring. So, for example, platinum is not very interesting, terribly. It's very pretty. There's just as much platinum as there is in gold, so why on earth, so why there's any difference in the price, who knows? But some of the elements are really curious and really quirky. Okay, I think probably the least interesting ones are probably the ones we've just discovered in the last sort of 10 years or so. So for example here, the last one that's currently been discovered is oganesson, and there's only about 5 or 10 atoms of that, and we don't really know a fat lot about it, so hard to get excited about it, apart from the name's quite cute. Why they use platinum instead of gold? Two different, slightly different reactivities, and they've got lots of different uses. They're not terribly reactive metal at all, which is why you use them in jewellery and stuff like that, and also in a lot of chemistry experiments where you don't want reactions going on, but you do need like a catalyst or a hot sort of electrode or something like that. How is it related to gold? If it's boring, it's just not very exciting. It doesn't do a lot of chemical reactions. Like, for example, unlike if you look at chlorine, for example, chlorine and fluorine, I mean, they react with everything. They're going to have to sink their teeth into everything and have a little go. So, for example, your Teflon, your pan, is xenon tetrafluoride, effectively. So it'll even react with totally inert xenon. Whereas platinum doesn't really want to react with anything. So it's safe to use. Yes, of course it is. Yeah, absolutely safe. So what I thought I would do is just a little demonstration, if you don't mind. Can I just show you a little funny demonstration on indicators as well, just before we leave today? So here is a little pack, look, of blue pea flowers. And this is actually a tea. What is the most dangerous element? Oh, by miles. So I'll just come back to that in a second. Sophia, the most dangerous element, I'll just go back to face cam for a second. Okay, by miles is polonium. That's hideously poisonous, hideously toxic, and very radioactive. You don't want to go anywhere near polonium at all. Really unpleasant. When you get a sec towards the end of the session, can you mention the person? Yes. So I've already just been told in the chat to remember that if you'd like, because you attended a MEL Science webinar, if you'd like a little personalised certificate from me, all you've got to do is click the link that's in the chat. Or it'll come up in the chat in a second, I think, Russell. Just click the link and you can get a little personalised webinar that says, hey, I think there's the link. The link is there. So you get a personalised link from me that says, hey, I attended this webinar, learned some interesting stuff, asked a load of questions, and it was good fun, I hope. Cool. So what I've done is I've put a few of these wonderful little pea flowers into a glass. I'm just going to add some hot water. Now this is a drink. You can actually drink this, so I'll show you that. So I'm going to put some hot water in this. Does the coronavirus have any of these elements? Leo, the coronavirus is a complicated, very, very, very complicated biological organism, and as a consequence it is made of RNA. And the genetic material that makes up the virus is RNA, so ribonucleic acid, and that's made of all sorts of different chemicals. The main ones, of course, phosphorus, hydrogen, carbon, a bit of sulfur, all that kind of stuff in the RNA, and then of course its coat is a phospholipid coat, and that's made of phosphorus and carbon and hydrogen and oxygen, stuff like that. So it's a complicated mixture of all the different elements. What's in that water? So this water, look, I've just poured into here some blue pea flower. So this is the blue pea flower, and this is actually a drink. You can actually drink this. And it's a really pretty, very delicate little pea flower, and it gives the dye comes out of the flower. And if I just show you this, okay? So this is the pea flower tea. So you can actually drink this, it's quite nice. And it's lovely, it's really tasty. But interestingly, this is an indicator. And if you watch carefully, look, I can change the colour by simply putting in some, I've got a little bit of yellow here, some lemon rather. If I put some lemon in, look, you can see the pea flower colour changing. So this is another natural indicator, look. So it's gone from blue to a kind of purple. How cute is that? Cheers! Very nice indeed. Ta-da! Okay. Is that okay? Did everybody have a bit of fun? Lily, that's so nice. Thank you very much, Lily. I'm delighted. I'm absolutely delighted. That was such a nice thing to say. Thank you very much, Lily. Your absolute pleasure. Franco. Sophia, oh my gosh. There you go. Yes, that's awesome. Thank you very much. And thank you, Ryder. Lovely. Sophia. Excellent. Delighted you had it. We loved your jokes. More jokes to come, so don't forget, every weekend, I think there's a break, there's next weekend, and then there's a couple of weeks where there's a bit of a break, and then we're back again Saturday and Sunday. And you are very welcome. I'm absolutely delighted that you guys, girls, you're very welcome. Thank you so much. Thank you for coming. Thank you for taking part. Thanks for your questions and your enthusiasm. Absolutely delighted to have you on board. So I'd love to see you next week. So stay safe. Enjoy the rest of your weekend. And I will see you, I hope, next week. So please, where are we going? So stay safe, and I shall see you next week. Goodbye.